We spent a lot of time this quarter learning about transition metal complexes, their structure, their properties, and how we can study and understand those structures and properties. But what we haven't talked about is actually the synthesis and functionalization of these organometallic complexes or transition metal complexes. And so as we get into that, we're going to think about how is it that we can change the ligands around a particular transition metal? How can we make predictions about whether a ligand will leave and be replaced, or if it will stay tightly bound to our metal center? So to start, we're going to look at this reaction scheme that's the replacement of a water molecule, right? So if we're starting with our hexa-aqua transition metal complex, right, a nice octahedral metal complex, and in the presence of an H2O or in the presence of an O18 label, we could actually measure the rate at which this exchange is occurring, right? At how fast are we swapping out the water surrounding our metal center with one of these O18 labels? And as it turns out, if we look at a number of different transition metals, we see that there's a huge variation in terms of how quickly this reaction can occur. So for example, if our metal is a chromium 3 plus center, right? If we have a chromium 3 plus metal here, this is an extremely slow reaction, right? So this is on the order of 10 to the 6th seconds per mole. And so that's a very long time to see any kind of transfer occurring or swapping of this radio label or isotope label into our transition metal complex. However, if we look at something like iron 3 plus, right, this is a very fast process. It's readily incorporated into the coordination sphere around our iron. And so what's the difference between these two, right? What's the difference between a chromium 3 plus and an iron 3 plus? Well, if we look at this, our d electron count is different, right? So for a chromium 3 plus, this is a D3 metal, whereas iron 3 plus is D5. We also know that water itself is a weak field ligand. This means that delta octahedral will be very small for these complexes. So if we think about our chromium 3 plus case, and we're going to fill in our ligand field, let's choose a nice bright green for our electrons here. There is no high and low spin configuration for our D3 metal. And we can see that all three of these electrons are sitting in our T2G orbital set. However, if we look at iron 3 plus, which is again a D5 metal, knowing that aqua ligands are weak field ligands, that means that this is more than likely a high spin complex. And this means that we have electrons that are both in our T2G orbital set and our EG orbital set. And as we talked about in our last class, right, this EG orbital set is actually antibonding orbitals. So in general, what we can see here and the extrapolation that we can make is that when we populate these antibonding orbitals, all of a sudden the bonds in our complex are weaker, right? So we have weaker bonds in our complex because we are populating these antibonding orbitals. And so this allows us to make some broad generalizations about what kinds of complexes are substitutionally inert, meaning they won't undergo substitution readily, versus complexes that are substitutionally labile, right? So the types of features that are in a complex that make them quick for substitution, right? So we're going to kind of arrange a spectrum here from inert, right, or unreactive, up to reactive, what we call substitutionally labile. And one of our key features is, again, just the presence of electrons in our antibonding orbitals, right? If we have electrons in those EG set of orbitals, then we're going to see a more reactive complex, right? So that means that things that are only have electrons in our T2g orbitals will be inert. So that means that over here on the inert side are going to be complexes that are D3, right? Like we saw with the chromium 3 plus. If we have a low spin configuration for D4, D5, D6, those will be substitutionally inert. D7 kind of falls in the middle, right? So it's a little bit more often, or that one reacts a little bit faster. So we can put that a little bit more on on the spectrum here. Another thing that's inert is if we have a square planar complex. So this was our D8 16 electron complexes with strong field ligands. So these fall in the range of our inert inert complexes, right? So if they fall into this category where we're really only having or filling up electrons in our T2g orbital set, they will be more inert when it comes to their reactivity. In the middle, we have our D7 electron cases, and if they're high spin D7, they definitely fall into the labile case. Another thing that falls in the middle here is weak field ligands or weak field complexes that are tetrahedral or square planar. So let's give ourselves some room here. So I'm going to move D7 down a little bit. So if we have weak field tetrahedral or square planar, right, these kind of fall in the middle. They might not react extremely quick, but they are still more reactive. So that means that our very labile transition metal complexes, ones that undergo reaction very quickly, again, are high spin cases of D4, D5, D6, D7. After D7, we only have the high spin configuration that's possible for D8, D9, and D10 complexes. Right, so if we have anything that's in those antibonding orbitals, they tend to be more substitutionally labile. In addition to this, we also have closed shell transition metals, tend to be labile. Right, so this is essentially D0 kind of cases. And this includes other things, you know, like sodium. So if we think about sodium plus is very labile. Barium 2 plus, right? Things that have our closed shell electron configuration tend to be very substitutionally labile and undergo these reactions very, very quickly. So again, this really just breaks down to the presence of electrons in our antibonding orbitals, in those EG orbitals, and then the inclusion of closed shell transition metals, right? Those all tend to be very labile. However, if we have low spin complexes, right, where we only have electrons sitting in our T2G set, those tend to be much more stable complexes that are inert to substitution. So a few other patterns that we can see when we're predicting whether a complex will be labile or reactive. A few more patterns we can pull from our periodic table. The first one is the charge density of a metal. So atoms or metals at the center of transition metal complexes that have a lower amount of charge density react much faster than those that have a higher amount of charge density. So we would predict, right, that the sodium cation, which we already know to be extremely fast, is going to be faster than something that has a 2 plus charge, like maybe a magnesium 2 plus, right? These are still closed shell, so they're still labile, but we're just comparing the rate of reaction, right? And magnesium would be significant faster than something like aluminum 3 plus, right? That has this higher amount of charge density, right? So the greater the amount of charge, the slower the reaction, right? So we go from slower to faster if we're making comparisons here, right? So this is going back to trends and thinking about the way that we approach periodic trends. All of the things being equal, we might be able to make arguments based on charge density. The other thing to focus on is the periodic groups, right? As we move down the periodic table, There's more covalency in our bonds, right? So the electrons are being shared between our ligand and our transition metal a little bit better, and this leads to slower reaction rates. So if we were going to look at the relationship between iron 3 plus, ruthenium 3 plus, and osmium 3 plus, we would find that the osmium would be the slowest because it's further down on the periodic table, right? And the iron would be the fastest here, right? And the osmium 3 plus, as you go down on the periodic table, this is something we haven't really talked about before, but lower on the periodic table almost always means a larger delta octahedral, which means we generally have low spin complexes. So as soon as you move away from that first row, your delta octahedral gets large enough that it's very, very rare for you to have a quick substitution that can occur, right? A large delta octahedral leads to low spin complexes as you move down on the periodic table. So again, if these are all D5 metals, like the iron, ruthenium, and osmium series that we've looked at, those are very likely to be the low spin configuration for the osmium case, even if we had an aqua complex or something that was a very weak field ligand. So how can we determine the nucleophilicity of a ligand? Well, nucleophilicity tracks very well with what we already understand from organic chemistry, right? So nucleophilicity, or how strong of a nucleophile something is, tracks well from organic. So what that means is, in general, if we have a strong base, right, this would be a good nucleophile. And a weak base would be a poor nucleophile. So we can actually construct just a list here. If you ever actually need to use this list, it will be provided for you, so you really don't have to memorize what this list is saying. But we can actually rank these from strong nucleophiles to weak nucleophiles. This also can kind of loosely track with the spectrochemical series for transition metal complexes. And so if we think about strong nucleophiles, right, this would be things like carbon monoxide or cyanide, right, tend to be up here at the upper end of our nucleophilicity charts, right? This is followed by phosphines, so PR3. So if whether R is alkyl or aryl, right, these are all reasonably nucleophilic when it comes to transition metal complexes. This is greater than a hydride. Somewhere in this ballpark is the acetic or the acetate anion, right, falls down about here. This is generally better than our halogen series. Which is in general better than water. And now we're getting down to where we have very poor nucleophiles, right? Water is better than ammonia, which is better than pyridine, right? So we remember the structure of pyridine. And pyridine is generally stronger than something like a triflate anion, right? These extremely weak bases that are down at the end of our nucleophilicity chart, right? And so we have this general list that describes things that are stronger nucleophiles for transition metals. Down to the end of our spectrum, which are weaker nucleophiles for transition metals. And so we can make some rough predictions about the nucleophilicity of a complex, right? So again, this is just thinking about a substitution. So if we went in with a chloride complex and we were to add acetate, right? We could imagine that we would readily replace those chlorides on the complex with our acetate ligands, because acetate is a stronger nucleophile than chloride, right? So it's pure, just simple substitutions that we can follow. Again, and this tracks reasonably well all the way back from organic chemistry. and thinking about the nucleophilicity of a transition metal complex. When we're thinking about this substitution, there's another important feature that's called the chelation effect. So if we're looking at the replacement or substitution of something like a pyridine from a complex, so let's imagine that we have a copper complex, it has a chloride on it, and it has two pyridines. Right, one of the few times in the quarter where I get to draw out my chemical structures versus a copper complex that has a bipyridine. The substitution for the two individual pyridines will be much faster. And this is due to something called the chelation effect. Right, so I'm going to write that this is slower due to chelation. So earlier in the term, we talked about bidentate ligands, right? These are also called chelating ligands that have multiple binding sites, right? So this means that there are multiple binding sites. And this makes it much harder to remove the ligand. Essentially, there's a thermodynamic driving force to keeping both of these nitrogens attached to the copper. If we were going to remove one nitrogen and replace it with another ligand, it's thermodynamically favorable just to reattach the nitrogen. Essentially, because it's locked in two places, you have to break both of those bonds in order to substitute the bipyridine. Whereas if you just have the individual pyridines, you just have to remove one copper nitrogen bond in order to replace it. So we have some general rules now where we think about the nucleophilicity of a complex, right? We can generally make predictions about what will happen if we add in a particular ligand, right, to our transition metals and whether we will get these ligands to be replaced. So again, we go back to our nucleophilicity ligand sets here, and weaker nucleophiles mean those would be replaced on a transition metal by stronger nucleophiles. So now let's talk about how we can actually make some predictions for the synthesis of these different complexes. We can make predictions about the substitution patterns for a transition metal complex using those nucleophilicity parameters. But what if we want to make a specific complex? So let's look, for example, at the synthesis of something like the molecule cisplatin, which we've talked about before. So this is an anti-cancer drug. It's a very potent complex. And it is important that the two chlorides end up cis to each other. And one way we can control the synthesis of these transition metals is through the use of what's called the trans effect. And this effect is largely limited to D8 square planar complexes, right? And so this is essentially a directing effect. So if we imagine that we have some transition metal, and I'm going to list two different positions here, T1 and T2. And I'm measuring the substitution on this complex, right, of a new ligand, so some L2. I'm going to pretend, right, that this substitution will occur and will replace one of my ligands marked L1. So that leaves me two options, right? Either L1 can end up trans to T1, or sorry, L2, our new ligand, can end up trans to T1, or it could end up trans to T2. And there's another series here of ligands that we can look up, and it has a very circular definition, right? And these are trans-directing ligands. And so ligand substitutions for these square planar transition metal complexes happen across from the stronger trans-directing ligand. Now, this is a circular definition, if you'll notice, right? It's saying it happens because we've observed it happens. And so this is actually an empirically derived list. So for our trans directors, this is not a list, again, that you need to memorize. If you're expected to use this, you'll be given some form of this list. So for our trans directing ligands, our strongest trans directors are hydrides and phosphines, which is better than iodide, which is better than CN or CO, or even methyl falls in a very similar spot in trans-directing ligands, over Cl minus, over amines, which are slightly better than other alkylamines, which is slightly better than pyridine. And so again, this is a list that you don't need to memorize, right? But just apply. So we don't need to commit these items to memory, but we do need to know how to apply them. So let's look at a case of how we can apply this. So I started with this example of saying, how is it that we could make, right? How is it that we could make cisplatin, right? How is it that we can make cisplatin? So let's pretend, right? Let's put on our thought experiment helmet, and let's pretend that in the lab, we have access to 4 different compounds, right? So our goal, right? I'm gonna write it up here so we remember. Our goal is to make cisplatin. And let's imagine that in the lab, right, we have access to the following reagents. So we have in there hydrochloric acid, HCl. We have a bottle of ammonia, right, or ammonium hydroxide if it's in water, right? We're not mixing these together, right? We're not trying to kill anybody or knock anyone out. In case you don't know, you don't want to mix strong acids and ammonia or bleach and ammonia, things like that. So we have HCl, we have ammonia, and we actually have 2 different platinum salts. So the first salt that we have is the ammonia platinum salt, right? And this is going to be the 2+ cation, right? So it has some anion that's on it. And we also have access to the tetrachloroplatinate that is also 2-. So both of these, right, are D8-16 electron complexes, and both of them have weak field ligands. That means that these are substitutionally labile. According to our rules from a few slides ago, right? So both of these can undergo substitution, but what we need to do is figure out how can I make cisplatin using my understanding of the trans effect. So let's start by thinking about what our approach would look like if we started from the tetraammonium platinum starting material, right? So if we start with our ammonium platinum, and we were going to treat this with Cl, right, or HCl. So we're introducing chloride ions into solution, right? HCl is a strong acid, so it completely dissociates in solution. We can go back and see that chloride actually falls a little bit higher on our nucleophilicity chart than ammonia. So depending upon our ratio here, we would predict that we would actually displace our or displace one of those ammonia with the chloride. And so what we would be left with is the first thing that would happen is we displace one of our ammonia with a Cl. And if we're following our charge through, right, we haven't done any redox chemistry on our platinum, so it needs to stay at 2+ center, right? So that means that it's actually just a positive charge on our complex. And so when we're looking at this structure, now we're looking at the addition of another molecule of HCl, right, or another chloride that's being added. So we actually have two different ligands now, right? We have a chloride and we have ammonia. And so we need to figure out which of these is the stronger trans director, a chloride or ammonia. So let's go back to our list, right? We see that here's chloride, which is actually one step stronger than ammonia. So we would predict, based on our trans-directing ligands, that the chloride is actually a stronger trans-director. Right? The chloride is a stronger trans-director. So that means that the complex that we would presume to form would undergo a substitution across from the chloride, because again, it is the stronger trans-director. And so here, right, we have now trans platin. I don't know if that's the name for it or not, right? But this is not the complex that we set out to make. And it's just because the chloride is a stronger trans director than the amine, right? It's a stronger trans director than the amine. And so we end up with this trans product. So let's see what happens if we start from our tetrachloroplatinate, right? If we start from our tetrachloroplatinate complex, and let's treat that with ammonia. Sorry, we're starting with the chloro. Now, the nice thing with this is ammonia does fall lower on our nucleophilicity chart, right? So we might predict that this reaction might be uphill. This is still a labile or substitutionally labile complex. It is weak field ligand, right? Chloride is a weak field ligand on our square planar complex. So this is just a matter of equilibrium and Le Chatelier. If we increase the amount of ammonia, eventually we'll start to see some kind of a reaction. And again, the first thing that would occur is the substitution of one of those chlorides with a molecule of ammonia. So we're left again with our three different Cls. And so again, now we're looking at the addition of a second unit of ammonia, a second ligand substitution that's occurring, right? This complex still has a minus charge on it, right? We want to keep our oxidation state of our platinum steady. The chlorides are X-type ligands, so if we have 3 X-type ligands and the platinum is 2+ in charge, that means that we would have a negative overall charge on our complex. So now again, we're looking at which of these is a stronger trans director, ammonia or chloride. Well, chloride is still the stronger trans director. That means that I would replace across from a chloride faster than I would replace across from an amine, right? So we are going to replace this chloride. So if we're treating this with excess ammonia, because the chloride's a stronger trans director, we would prefer to do a substitution that is across from a Cl than a substitution that's across from an NH3. And so now we've actually gotten to our cis-platin complex. So using the trans effect, right, we can make some predictions about how we can get particular transition metal complexes. Using our nucleophilicity parameters and our understanding of labile transition metal complexes, we can start to propose some syntheses of other potential transition metals, right, as we understand and think about these trends in nucleophilicity. All right, so we're going to get some practice with this, and we're going to have a good discussion this week in class as we dig into some literature in the field of inorganic chemistry. Thank you.